In this lesson, we're going to go through double angle identities. So these identities are the next set of identities that can be found on your formula sheet. So these are this last group here at the bottom of your formula sheet. And these have to do with exactly what they sound like. We are doubling angles. So I'm just going to show you first. These are our double angle identities. So we have sine of 2 times an angle is equal to sine A times cos A. Cos of 2 times an angle is equal to cos squared A minus sine squared A, not to be confused with one of our first identities we learned, which was sine squared theta plus cos squared theta, which is equal to 1. This is now subtraction. And then you can see here we've got 2 variations of that identity. And tan of 2a is 2 tan a over 1 minus tan squared a. So if ever you see this 2 in front of your theta or your variable, you know you're working with double angle identities. So I'm just going to show you where some of these come from. So in example 1, it says derive the identity for. So we've got sine 2 theta, cos 2 theta, tan 2 theta. And basically what we're looking to do when it says derive, it means show where these identities come from. And to do that, we can use other identities. So we know that sine of 2 theta is the same as sine of theta plus theta, because it's the angle plus itself, or the angle doubled. Now, we just learned in the last lesson that sine of an angle plus another angle is equal to sine A times cos B plus cos A times sine B. So you can see that I've just replaced that here. And then what you'll notice is that these sine theta cos theta plus cos theta sine theta, we could just switch these around, and essentially this is 2 times sine theta cos theta. So that's where this double angle identity for sine comes from. For cosine, very similarly, we can use our sum identity. So 2 theta is the same as theta plus theta. And then we can substitute that in to our sum identity for cosine. So cos A, cos B minus sine A, sine B. So you get cos theta minus sine theta, or cos squared theta minus sine squared theta. So that's where this identity comes from. And finally, with tan, we can do the same thing. So tan of theta plus theta, and then again using this identity here, tan theta plus tan theta over 1 minus tan theta, to get 2 tan theta over 1 minus tan squared theta. So really, this set of identities here, these double angle identities, are really just derived from all of these identities that we've learned so far. So we can look at example 2 here. You'll see we've got if sine theta equals 3 over 5, and theta is between 0 and pi by 2, which essentially means that we're working in quadrant 1. Find the exact values for sine of 2 theta. So here basically we have some unknown angle where we know that it is equal to, or sine of that angle is equal to 3 over 5. We want to know what would the sine value be of double that angle. So for example, if the angle was 30 degrees, what's the measure at 60 degrees? But here, these angles aren't necessarily special values right off of your unit circle, so that's why the double angle identity comes in handy. So if I use sine of 3 over 5 and I make my triangle, y is 3, and the hypotenuse or the radius is 5, that means the x value is 4. So what that means is that sine theta was 3 over 5, and cos theta is 4 over 5. So if I use my double angle identity, sine 2 theta is equal to 2 times sine times cos, so that's just my identity from my formula sheet. I can then just plug in these values. So I can plug in 3 over 5 for sine theta and 4 over 5 for cos theta, and multiply we get 24 over 25. So that means if I took this original angle that was here and I doubled it, so whatever this measure was, say it was 25 and I doubled it to 50, then this is now the sine value. And I can do the same thing for the cos value. So the double angle identity for cos 2 theta, is cos squared theta minus sine squared theta. So then I just plug in cos and I plug in sine. I square both and subtract. I get 7 over 25. Now I can also use these double angle identities in proofs. So in example 3, you'll see here that I've got a proof. It's asking you to prove this 2 tan theta over 1 plus tan squared theta is equal to sine squared theta. So now that you know your double angle identities, what I would do first is on the right hand side, rewrite this as 2 times sine theta cos theta. From there, it's up to you how you proceed. In my proof, what I chose to do was on the bottom here, 1 plus tan squared theta is equal to secant theta. So I prefer in a denominator if it has 2 terms. If you can make it into 1 term, that's really helpful. So I changed this to secant squared theta. Then on top, I tried to get everything in terms of sine and cosine. So tan is sine over cos, and secant squared theta is 1 over cos. Flip and multiply, and you'll see we get canceling of the cos on the bottom, and we're left with 2 times sine theta cos theta. So we've proved this identity. Very similarly for question B, again, my first step was cos 2x. I rewrote as cos squared x minus sine squared x. These double angle identities, when you're working in a proof, it makes the most sense to first change those into their corresponding value and then work on the other side. So here, what I did here was I actually split up the 2 terms. And the reason that I did that was because over here I saw that I had 2 terms. So if I just write 1 over secant squared separate as 1 term, and then minus tan squared over secant squared as a separate term, then I can see right here 1 over secant squared theta is cos squared theta, which is what I need. And on the other part of this, I get sine squared over cos squared over 1 over cos, and again, those cancel to leave me with sine squared x. So that's one helpful tip. We haven't seen too many of these yet, where you actually split up your expression into 2 parts so that you have 2 parts just like the right hand side. And finally, example 4 is a little bit different. So it says on the unit circle, if p of theta is equal to 0.588 and 0.809, find the coordinates of p of 2 theta. So I've shown 2 different methods here. The first thing that you can do is basically you have here sine theta and cos theta. So if you want to find p of 2 theta, p of 2 theta is going to be cos 2 theta, sine 2 theta. So I can take these values that I know and solve for cos 2 theta and sine 2 theta. So cos 2 theta is cos squared minus sine squared. So cos squared, I just realized I wrote this backwards, sorry. That was a rookie mistake. This is cos theta, sine theta. There we go. Okay, so then I just plug these values in. So 0.588 squared minus 0.809 squared, and I get my cosine value for cos 2 theta. And then sine 2 theta, same thing. I use the identity and I plug in those values. I then get cos 2 theta, sine 2 theta, and that's my coordinate for, and I should label this is p of 2 theta. So that's one option. Another option is to actually solve for theta. So here what I did was cos theta was equal to 0.588. So I actually solved for what theta was equal to. So theta was equal to 54 degrees. And then I used a calculator to then solve for cos of 2 times 54, or cos of 108. And I just did cos 108 to get those same values. So it's up to you how you choose to solve this. This one shows more of your understanding of the double angle identities, but this one also works. So try out some practice questions. There's a few in your textbook, there's a few in your extra practice, and there's some in the PreCal review booklet.